Welcome to another video in the series about the C7000 compiler. This video introduces vector data types. My name is George Mock and I'm your guide. This video opens with an example that demonstrates why vector data types are a feature of the compiler. And examples like this, gloss over lots of details and don't explain everything, and they just kind of move very, very quickly. So don't expect to, deeply understand it all. Let's just kind of take a high-level view just for a moment, and then we'll slowly descend into a bit more detail. So I want to have you look at this first example. It's code that uses just a standard type that you're used to, float. You've seen it many times. You've seen code like this many times. This does exactly what you think it does. Now here's some equivalent code that uses a scalable vector data type called floatvec, okay, and it's in the C7X namespace. For those of you who are not familiar with C++, that's what this looks like. Okay, floatvec is a type that is available inside the C7X namespace, and that's how you use it. We're creating three different vectors of that type, and here we're adding them together and assigning them to a result. The whole point here is to get code similar to this. These are instructions that are available on the C7000 CPU. These are the reasons why people like to use that C7000 CPU. This instruction is loading the entire vector all at once into a register wide enough to hold it. Okay, same for that, another load instruction. This add is doing 16 32-bit floating point additions all at one time. Okay, powerful stuff. This is excellent stuff, and then of course we're storing it all with one instruction. Using vector data types makes it much more likely that you're going to get the code like this. You're going to get the architecture entitlement that you want to get out of C7000. So this game, if you will, this goal is really what we're going for, and why we introduced vector data types into the C7000 compiler. I'm about to give you some good advice, but in an unusual way. So the good advice is prefer scalable vectors. The unusual thing about it is that scalable vectors are not described in this video. Which, what's going on? What are we doing here? Okay, well, this video introduces concepts which scalable vectors are built on, okay? And to do that, I'll show you several examples, and those examples, while correct, are not typical of code that you see in C7000 programming in the field today, or really any time in the future. Nonetheless, these examples and these concepts are the best place to start, even though you don't stay at this conceptual level for very long. A rough analogy is compare arithmetic to algebra. So arithmetic is, like the first sort of math you learn, your 1 + 1 = 2 sort of examples. But eventually, after you get all that sort of arithmetic down, you move on to algebra, where you start talking about A = B + C, solve for C, or whatever you're doing in algebra. So this video is sort of at the arithmetic level, okay? Scalable vectors are at the algebra level. Even though we don't talk about them in this video, this is a necessary step into moving on to the scalable vectors that will be discussed in a later video. Here is a table of information about vector data types. I will walk through one row in the table with the idea of explaining to you what each column represents. So let's go through the first row. Why not? Syntax is what you write in the code. Char, that n will be replaced by a number. There's an example on the very next slide, so you'll see what that looks like. So how many, and that number represents how many chars are in this particular vector. The second column element size is the size of a single element in bits, so char is 8 bits. Signess is something that applies in the case where the representation is an integer. Is it signed or unsigned? representation will be either integer, floating point, or Boolean. And then the last column, max elements, 64 is the maximum number of char you can have in a single vector. Okay, so as a point of comparison, let's go through another row. Float looks like a good one to go through, so let's look at this. You would write float. N is a number not to exceed 16. That's the maximum number of elements for a float vector. Each element of the vector is 32 bits wide. Signless doesn't make sense in this case because the representation is floating point. So I hope this is starting to make a bit more sense now. This slide walks through each column more specifically. So again, the first column is syntax. What do you write in the code? N can be replaced with any of these numbers. That's where you're specifying how many of those elements are in this vector. Let's take a look at a specific example. This one's ushort2. That's the name. Excuse me, the name of the type. SV2 is the name of the variable. So this is two 16-bit unsigned short elements. The total size is 32 bits. Let's consider the second example. It's a long. There's two of these in this vector. That's the name of the variable. Two 64-bit signed long elements. A long is 64 bits on C7000, and so two of them comes to 128 bits. The next column, element size, the size of one element measured in bits. The next column, signless. In the case of an integer representation, is it signed or unsigned? The next column is rep, which stands for representation. What do the bits represent? And there are three choices: integer, floating point, or Boolean. The last column is max elements, the maximum number of elements that are supported for that type. Now, one point of confusion I want to avoid right away is that this maximum number may not be the best size vector for your specific CPU. Okay, so just because you can use 16 ints, say, that doesn't mean 16 ints is the best choice. It could be a different choice. I don't want to get farther into this detail in this particular video. There's going to be a whole other video about scalable vectors, and they are the long-term solution to what I'm hinting at right now. Okay, so now that we understand what the columns represent, I'm going to give you another look at the table. This might be something you want to pause the video or take a screenshot or something like that. Vectors of complex types are supported. Here's an example. You'll write a C in front of the base type, and then 2's the number of them that there are in that vector, just like you're used to. So C float 2 in this example, that's the name of the variable. So this gives you two 32-bit complex float elements. The total size is 128 bits, and that's because each element contains a real float and an imaginary float. Okay. There are other complex types available. Some examples are C44, C16, and so on and so on. Please consult the compiler manual for all the details. Vector literals, or how do you initialize a vector with constants? Here are some examples. A short with 4 elements. You write the type name here, list out the constants. For a float 2 example, looks like that. Suppose you want to initialize a vector where all the elements have the same value. That looks like this. This will initialize all 4 of the elements of this vector with the value 1. Vector concatenation, where we're talking about initializing a vector with C variables or shorter vectors and combinations of those. So here's some examples. This one, we have a int2 vector, and we're going to initialize it with A and B. They are arguments passed into this function. That's what that looks like. This next example, we're combining, initializing a vector with two elements with an argument from the function and a constant, and we repeat that with this second example with a different argument. This third example, a vector with 4 elements, we are initializing it with 2 shorter vectors. Now keep in mind, throughout all of these, you have to match, the number of initializers with the number of elements in the vector. Vector operators, we're talking about the C operators that you can perform on vectors. All the usual suspects are available. They're similar to the C operators that you're used to on non-vectors. So this first example is somewhat similar to the motivating example that I showed at the very beginning. We're adding 2 vectors together and assigning them to a result. Unary operators are available. So starting with a vector with these values, and then we apply the unary negative to it, that's going to give you the negative result, all those guys. Postfix operators are available. So again, we start with a vector that's got 1, 2, 3, 4. We apply the postfix, add 1 to it. A is each element of that vector, went up by 1. The original, A gets copied to B, and then the increment happens. So just like you're used to with post increment. And there are more of these. Please see the manual. I'm not going to cover all of them in this video because I think you get the sense of how these all work. Now there is one difference worth pointing out. In C operators on non-vectors, on scalars, the types don't all have to match. You can mix, signed and unsigned and float and all that sort of thing in the same expression. And implicit conversions are defined for that sort of situation. When you're working with vectors, there are no implicit conversions. All the types have to match, or it will be rejected at build time. Vector accessors are a method for accessing individual elements of a vector. You can use accessors to read or write, and they are written as suffixes to a variable name. So here's our getting to be our poster child example. We initialize a vector to 1, 2, 3, 4. This accessor right here, your .x, looks like a function call. Picks up the first one and assigns it to that variable. Okay. S3, remember we said we can use these to write, so S3 appears on the left side of an equal sign. It means that the 0, 1, 2, 3, this guy changes values from 4 to the 8, here. And then there's several different variants, and we're gonna look at some of them, not every single one, but we're going to look at some of the variants. Here are 2 variants of the vector accessors. The first one, they look like, .x, y, z, or w. This is for accessing an element of a vector whose length is less than or equal to 4. So, again, our favorite example, initialize a vector of length 4 with the values 1, 2, 3, 4. And then we pick up y and we pick up w. Well, what does that do? Well, it picks up the second one and the fourth one. They get multiplied together, and that'll assign 8 to var. Okay, so .y accesses the second element, .w accesses the fourth. Okay, let's take a look at another variant, .high and .low. .high accesses the elements in the upper half of the vector, and .low accesses the elements in the lower half. Okay, so let's look at our example. We initialize a vector of 8 elements to 1 through 8. Okay, and then we use the .high accessor to assign it to a vector of length 4, so half the size. And that means that, you know, the ones in the high half, 5, 6, 7, 8, is what gets assigned to vec high u4 here. And then we repeat it with dot low, and it works pretty much as the way you expect. It picks up these 4 and assigns them to that vector. Here are a few more vector accessors. So S019A, all your hexadecimal characters, you can use these accessors to access one of up to 16 elements in a vector. You can also write .s brackets n, or n is a constant, 0 to 63, or a variable, and this is how you can access one of up to 64 elements in a vector. If you ever want to write a loop that prints out, say, each element of a vector, this would be probably the best guy to do that with. You could put, you know, s of I in there. Dot even and dot odd, these are more of a grouping of a vector, sort of like high and low that I showed on the previous slide, but it's giving you the even and the odd elements, where the 0th element is even. And there's a few others that I don't describe in this video, but they are in the compiler manual. Supposing you need to convert one vector to another kind of vector, well, how do you do that? Okay, well, the typecasting syntax that you're used to, you know, with ordinary non-vector variables, that is not supported. You have to use a function that is named convert destination type, and then in the parentheses the source type. And here's an example. You know, we form up a vector of 2 integers, int2, and then we convert it to a short 2, and that gets assigned to a short 2 vector named vec s2. Okay, this works element by element. Okay, and one constraint that has to be observed is the vectors must have the same number of elements. If they don't, that gets rejected at compile time. Reinterpretation functions look similar to conversion functions, but they're actually quite different in terms of what's happening. So let's talk about this. So you use functions named as destination type, source type. So the syntax is similar, but what's happening is the interpretation of the bits changes. So how the compiler, you know, views the bits inside these guys changes. The bits themselves do not change at all. It's important to understand that, okay? And so the number of bits in each type must match, or you get an error at compile time. So let's look at our example. We'll start with a vector of length 4, initialized to 1, 2, 3, 4. You've seen that before, okay? As int2, so we're changing this guy. We're reinterpreting it as a vector of length 2. And it's important to notice these are the same size. So 4 shorts are the same size as 2 integers. And so this is the value that gets assigned to each element in vec i2. Okay, so that's where the 1 ends up. There's the 2, you know, 16 bits later, and so on. Okay, so that's how that happened. This next example, vec s4, we're trying to reinterpret it as a char4. Well, those are different sizes, so this gets rejected at compile time. I want to close with 2 references. The first one is this web address here. Obviously, one way to get there is to type that in. There's probably a few of you typing it in right now. Others of you probably think that's inconvenient, and if that's you, you are welcome to do a search on C7000 compiler. I tried that search with a few different search engines, and I always got this back as the first result, so that's another way to go. If you get to this video from the collection of C7000 compiler videos on ti.com, that page also has a link to this web address, so yet another way to go. No matter how you got there, once you get to this web address, you are on the home page for the C7000 compiler. That's where you can download the compiler, access the manual, and other details like that. The second reference is to e2e.ti.com. This is where you can go to ask any question on any TI product, including questions about the C7000 compiler. If that question happens to be related to a compiler or any related tools, it will be answered by me. Thank you for watching this video in the series about the C7000 compiler.